Well, guys, I really hope you had a very good weekend. I actually just drove in the nick of time. Yesterday, returned from Connecticut, just 1 minute past the time I had to record the lecture. Wonderful. Ping, ping. What about the rest of you? Good morning. Irvin. Morning, Gabriel. All right, so the derivative of, yes, that's right. The derivative of 7 to the power of x, it's going to be 7 to the power of x ln of 7. Now, it's easy to forget. I mean, you might just say, oh, I just remembered it. How do you remember that idea? Well, you do not like to take the derivative of 7 to the x. Am I right? You prefer exponential. So what you can do is, instead of 7, you can write e ln 7. That's where the ln 7 comes, and that would be to the power of x. Do you agree that if I take e and raise it to the power of log base e of 7, I will get 7? Are you with me? So I need to take the derivative of that, but what can I do here? I can move the x by multiplication. Here the x can be placed here, and so I am dealing with the derivative of ex ln 7. Yes, and that's very nice because this ln 7 is nothing more than a number. It's number times x. The derivative of a number times x, that number is the slope already, right? So it is just by chain rule. By chain rule, it would be e to the x ln 7 times the derivative of what you have in the power, and that is just a linear equation. It's a line that has ln 7 as its slope. So I got that. And then I can convert e to the x ln 7 back to what it used to be, to 7 to the x. Look at it, 7 to the x is ex ln 7, right? So I can just simply write here 7 to the x ln 7. Please in the comments confirm that you understand this idea, guys. I mean, not just me writing it out, but you could have figured it out on your own, correct? Good. Zainab, one more time. Again, I do not like taking derivative of 7 to the x, maybe because it's easier for me to remember that the derivative of e to the x is e to the x. Now, the derivative of, so I can convert 7 to the x to e form, because 7 is e to the ln 7, right? I can do it this way. 7 is e to the ln 7. So 7 to the x I can view as e to the power of ln 7 to the power of x. And then that is that's very similar to something like 3 to the power of a to the power of b. I'm just using 3 just arbitrarily, right? And that's 3ab. So that's what I do here with the x. I move it in. Good? With me? And taking the derivative of this expression is not so bad, because e to the x ln 7, it's the derivative, the outer function is the natural exponential, and its derivative isn't changing the function. So it's ex ln 7. And then the derivative of the inner function is simply ln 7. X times ln 7, take the derivative of that, you just get ln 7. Do you agree? Because ln 7 is a number. And x times ln 7, if you think about it this way, it's just a line that goes to the origin with slope ln 7. I hope that's clear. Now, I asked you to take the derivative of log base 7x. How do I do that? So I showed you the geometric idea, but just to save time, I will do that using just implicit differentiation, right? Implicit differentiation tells me I can do this. Y equal to log base 7x. So y is that function that has this name. And what do I know about log base 7 of x? I know that if I place it over 7, if I place it over 7, I will get x. So I will say 7 to the y is equal to 7 log base 7x, which equals to x. And then by implicit differentiation, I want dy dx. So I will have 7 y ln 7, that's the derivative of 7 to some power, right? Times the derivative of y by implicit differentiation is dy dx. And that would be equal to 7y ln 7. Well, actually, so let me not write this. Let me just write, it will be equal to the derivative of x, which is 1. Are you with me? Now, 7 to the y is just x. Look at it. 7 to the y is x. So this guy is just x. So what do I get? I get that dy dx, the derivative of my dy dx is the derivative of log base 7x, equals to 1 divided by x ln 7. Good. And let's now review the same thing in this lecture here. Okay, so we did the geometric idea. Now, with the geometric idea, e to the x and ln y are actually the same shape, the same graph. If I think of it, if I know how to take the derivative of e to the x, I know how to take the derivative of ln y with respect to the y-axis, right? And that's what I do over here. So you see that the guy on the astronaut walking on the y-axis is seeing the graph of ln y. For any y, the altitude is ln y. And, and the only reason that we have different derivatives is that they measure different slopes, the reciprocals of each other's slopes, right? The product of the slope measured by the astronaut on the y-axis and the astronaut on the x-axis is equal to 1, because this guy will think that horizontal is dy, and this guy on the x-axis thinks that horizontal is dx. Their notion of horizontal and vertical are entirely inverted. You understand that idea, guys? So then that means that I can take the derivative with respect to y of ln y this way. The derivative of ln y is the same as dx over dy. It's dx over dy, vertical over horizontal, rise over run. For this guy, vertical is dx. And that's the same as 1 over dy dx. Which is this guy will measure dy dx, so he will measure the dy dx equal to e to the x. So this guy will measure the y on the y-axis. He measures it to be 1 over e to the x, which is 1 over y. Guys, am I talking to myself, or you understand what I'm saying? Let me know. It's a bit hard, because you see the geometry thing and maybe implicit differentiation, you kind of can carry out the calculation and get to the right answer, but I hope you see what's the purpose of this calculation. With this calculation, I can actually see what's the reason of this 1, right? I can actually see much deeper into the subject. Okay, so that's using the same thing with implicit differentiation. Yes, Alex, e to the power of x equal to y in that calculation. You see, I just calculated d dy of ln y.
That is a very...
Yes, so makes sense. So dy dx is e to the x, and measuring on the y-axis, I calculate just the reciprocal. It's an idea that is difficult to communicate. It's very easy to be, so to speak, confused with the y and the x, but really it's just an inversion of perspective. What's vertical is horizontal for the other guy. What's horizontal for the first guy is vertical for the second guy. Good. They just do not agree. Their notion of horizontal and vertical are swapped. That's why they measure different derivatives, because they're in essence just measuring different slopes, but they're talking about the same curve. Okay, so from the geometric point of view, there is no difference between root of a root function and the square. Okay, they are kind of the same curves, and no difference between logarithm and exponential. They are the same curve. Okay, and we already calculated using implicit differentiation and other ways. We calculated the derivative of log base a of x, correct? I have to move on. We know this is the derivative. Yes, guys, you understand how to get to such ideas. Now, here is something that I would like to show you. Now, imagine that you are asked to calculate the derivative of this very ugly expression, the 7th root of x to the 4 plus 25 times x plus 1 to the 8 divided by x to the 6 and x squared plus 1 to the 100 and e to the 5x. Okay, so you might try to carry out the calculation directly, but you will waste a lot of time. There is something known as logarithmic differentiation. Okay, so what you do is this. Look carefully. Right? Do you remember the logarithmic rules, right? Is that if I take logarithm of a product, I get sum of logarithms. If I take logarithm of quotient, I get difference of logarithms. I'm going to exploit this fact. So here is what I will do. So I can set y equal to that expression. I want to find dy dx, yes? But it's much nicer for me to find the derivative of ln of y. Because look at it, I'm going to take logarithm ln of y on both sides. And why? Because I want to exploit that there are lots of products and multiplications to simplify everything, right? Do you see that? I apply logarithm, and what do I get? I get that it is, can you see, guys, that I get 1 over 7 logarithm of x to the 4 plus 25 plus 8 logarithm of x plus 1. Do you see what happened here? This is the logarithm of the numerator where I drop the power and multiplication becomes addition. Can you see that, or do I need to show you slower? Please write in the comments before I proceed, and do it fast so I can cover a lot today. Right? It's logarithm of numerator minus logarithm of this minus comes because this division will have everything on the bottom will be subtracted. Okay. Good. Logarithm of top minus logarithm of bottom. But the logarithm of top can be broken into 1 over 7 logarithm x to the 4 plus 25 plus 8 logarithm x plus 1. And then the bottom is subtraction, because it's this plus this plus this, right? Bottom it's 6 logarithm of x plus 100 logarithm of x squared plus 1 plus logarithm of 5x logarithm of e, when logarithm of e is 1. Okay, that's what happens here. And because there is a division, I subtract all those quantities. Good. So I have 1 over 7 logarithm of x to the 4 plus 25 plus 8 logarithm x plus 1 minus 6 ln x minus 100 ln of x squared plus 1 minus 5 to the x. Everybody says what I did before doing any calculation. I converted it to a much simpler formula. And then using implicit differentiation, if I take the derivative on the left, I get 1 over y, y prime. Y prime is what I seek. And y is equal to this full ugly expression. Yes? 1 over y, y prime. Now, what's the derivative of this expression? It's going to be x, it's 1 over 7, x to the 4 plus 25. The derivative of x to the 4 is 4x cubed on the numerator. I use chain rule. So it's 1 over what you have on the inside multiplied by the derivative of the inside. Here, it's 1 over x plus 1. The derivative of x plus 1 is 1. Here it's minus 6, 1 over x. Here it's minus 100. On the bottom, x squared plus 1. Derivative of x squared plus 1 is 2x. And then the derivative of minus 5x is just simply minus 5. We will solve a few exercises shortly, but do you get what I did here? Yes, guys? You understand what happened? It's just chain rule. and it was simpler than dealing with the expression originally. When you have lots of products and quotients or powers, applying logarithms before you take the derivative makes the calculation simpler. So then what is y prime? Y prime is y multiplied by the entire thing. Okay? And I think I forgot to write whatever follows. It's this original function multiplied by this expression. Okay, whatever is in the parentheses. What you see, this y is this thing. So it's original function multiplied by the derivative of its logarithm. That's what ends up being the case. Make sense? So let's see an example, and you will try to differentiate it. Okay, guys, here is your task. Differentiate x to the 3/4 root of x squared plus 1 divided by 3x plus 2 to the 5th power. And we'll do it together, but first your turn. Okay, bud, thank you. Let's see. Okay. Okay, Christian, good. What about the rest of you guys? All right, so let's do it together, I suppose. It's a bit uncomfortable to write in the text, I presume. So first trick, are you there, guys? First trick is to write y equal to this expression. And then what I will do is I will take logarithm. So I will write ln y. You could have written with any other logarithm, but it's easiest to take the derivative of ln y. Ln y is, let me just do it one time slowly. So it's x to the power of 3/4 root, and root, by the way, is 1/2, right? I'll write root like 1/2. X squared plus 1 to the power of 1/2 minus ln of 3x plus 2 to the power 5. Now this is a product, so that would be ln of this plus ln of that, and then I can drop the 3/4. So it will be 3/4 ln x plus 1/2 ln x squared plus 1 minus 5 ln of 3x plus 2. Are you with me? Great. Good, good. And then you take the derivative of that expression. The derivative of that expression will be, so I'll just write line and prime. So that would be what? That would be 3/4 1 over x plus, what do you have here? You have 1/2 x squared plus 1. The derivative of x squared plus 1 is 2x. I can simplify the 1/2, all right? And then minus 5 times 3, so it's 5. And here we have 3x 3x plus 2. All right, that's the derivative here, and that derivative equals to, so this is what we in essence have. We have 1 over y y prime equals to, what was that over there? It equals to 3 over 4x plus x over x squared x squared plus 1 minus 15 over 3x plus 2. And all that remains to be done is that y prime equals to y multiplied by the full expression. And remember what y was. Y was this. So it's x to the 3/4 root x squared plus 1 divided by 3x plus 2 to the power of 5 multiplied by 3 over 4x plus x over x squared plus 1 minus 15 3x plus 2. Good? We are done. That's the solution to this question. All right, let's continue. Here it's written out. Now, here is a remark. Technically speaking, when we apply ln to y, it is implicit that y is bigger than 0 because logarithms do not work for negative numbers. So the expression that I apply to, I have to kind of sense that it works, that this derivative works for only its positive sense. That's on y positive. Okay, so in this case, for example, in the case where I applied it, look at it, 3/4, I cannot take a quarter root. I cannot take the fourth root if x is negative. So I cannot plug negative numbers. And if I plug positive numbers, clearly that will work. Good? That's technically speaking. And there is another example. Let's say the derivative of x to the alpha is alpha x to the alpha minus 1. And again, you might kind of remember this rule, but we only proved it for integers and maybe for 1 over 2, 1 over 3, 1 over 4, right? So you see when you can prove it. We had this, remember Oscar Wilde and the rose and the nightingale, or the nightingale and the rose, yes? So we used the difference of n powers that to prove the power rule. So the power rule we established only for polynomials, only for integer powers. And then we used other tricks to figure out what's the derivative for roots. Yes? The most logical trick was actually to say that a root of a function, let's say x to the 1/3 is very similar to x cubed. It's the same curve. And the slopes are going to be the same. And I can use that idea to figure out the derivative. But in general, what happens if alpha is an arbitrary number? For instance, what does x to the power of pi even mean? Right? X to the 1/2 means take the square root. But what is x to the power of pi? Okay. So we may define, of course, x to the alpha as e to the alpha ln x, because we do understand what it means to exponentiate using the e. I hope you remember, guys. E to the x, it's simply 1 plus x squared over 2 plus x cubed over 6. It's an infinite polynomial, right? So when I just write it as e to the x, that's only because I see analogies. It behaves in other instances very much like an exponential function. That's why I write e to the x. But really, what do I do when I say e squared? I write 1 plus 2 squared over 2 plus 2 cubed over 6 and onwards, right? That's what e squared is. And this is true for all numbers. So e to the power of pi is 1 plus pi squared over 2 plus pi cubed over 6. And this summation is presumably unambiguous. Do you follow? We are only using here elementary operations. I understand what is e to the pi. So when it's e to some power, I understand it pretty well. Okay, so x to the power of alpha is simply e to the alpha ln x. Does it make sense? That's how I can define it. And because logarithms are meaningful, just because exponentials are meaningful, this expression is fully meaningful, and I can differentiate it. You understand? Guys, before I continue, just I want to see, and honestly, you don't have to worry about it. Just honestly, do you understand what I have just said? Okay. All I'm saying is that when you really think about it, you realize that you know, when you're using this power rule, you're being rather careless, right? When you just say that the derivative, you are correct, you end up being correct, but you are carelessly correct. It's like you walked like in Charlie Chaplin, right? You just walk, you're completely oblivious to the dangers around, and you're walking at the ledge of a precipice. So x to the alpha, the derivative is alpha x to the alpha minus 1. The formula is correct, and you might have used it carelessly all the time. But when you wonder what it even means, you are stuck even at this point. What is x to the power of pi? How can I interpret it? What am I really differentiating? Good. So what I'm saying is, because I hope you understood how I established the exponentials. That's one of the crucial ideas in this class. How I figured out what's the natural exponential, and I had it as an infinite polynomial. So that procedure is somewhat less ambiguous because I understand what it means to multiply, and I understand what it means to add. Okay, so I can understand what is e to the pi. So in general, x to the alpha, I can think of it as how do I get x? I get x as e to the ln x. So, right, so this is going to be the definition I pick for x to the alpha. Okay, which makes sense because logarithms make sense because they are just the other side of the coin. It's the same function, just viewed from a different angle, right? Logarithms make sense, and exponentials make sense. And then when I take the derivative, it's e to the alpha ln x times the derivative of alpha ln x, which is alpha over x. Now e to the alpha ln x is x to the alpha, and then times alpha over x. I can kind of simplify. I can subtract. It's alpha x to the alpha minus 1. You see, so the rule continues to work for all real numbers. That's how I can establish it, right? Because I'm just saying that there's well, there's still kind of lots of other issues if you're interested, but I will not continue confusing you further. I hope you understood what I said. Okay. Now, will you please take the derivative of the following functions? A, y equals to logarithm of absolute value of x. What is the derivative of that function? In A, please write it very fast, guys. We are running out of time. Alexa, okay, thank you, Kirill. Alexa, almost right. Okay, so I will show you, there is a small mistake there. Right, absolute value is always something kind of scary, right? Consider absolute value is a piecewise function. Consider whether we are on the positive x or on the negative x. What are we differentiating? Okay. And come on, guys, only 3 people. I want to see all of you participate. Semester is soon over. Are you terrified about the final, which will come? I hope you are absolutely not terrified, of course, right? Because you understand the material. All right, let's carry it on together. What is absolute value of x? So ln of absolute value of x, it's really what? It's really the same as ln x if x is bigger than 0, and it's ln of minus x if x is smaller than 0. Do you agree? Right, so I don't like absolute value. It's kind of not convenient, right? So let's consider what's the derivative if x is positive. So the derivative where x is positive of ln of absolute value of x is the same as the derivative of ln of x, which is 1 over x. So when x is positive, it's 1 over x. You're with me? Now, what is the derivative when x is negative of ln of absolute value of x? Well, that is the derivative of ln of minus x. So we involve chain rule, so that would be minus x and then minus 1 in the numerator. You agree? And still I get 1 over x. So, and notice guys, when x is negative, I'm getting 1 over the negative number, right? So, so the derivative of ln of absolute value of x actually is 1 over x. Do you all understand? No matter where I look, it's going to be, in other words, if I zoom in at any number, positive or negative, it will be 1 over that particular number, positive or negative. Is it clear? I hope it is. That's going to be important in the chapter on integration, which I hope to begin soon. Integration is our most important topic, guys. There would be one lecture, I think, or so. There are going to be two the topics, okay, that are extremely hard. I mean, I don't know how many lectures can be spent on it. Actually, from my experience, it's almost futile to spend the lecture, on that topic, and that would be applications, optimization, and related rates. I will explain related rates. Optimization, I will show you my videos, and we can discuss that later. Okay, it is somewhat like delta epsilon. So see, I spent whatever 3 lectures on delta epsilon. How many of you understood it? All right, so b y equal to ln of sine x. What's the derivative? You see, we already know the derivative of ln of absolute value of x. So the derivative of ln, absolute value of sine x, is going to be, when I take the derivative of ln absolute value, it's 1 over sine. Yes, very good, very good. So what do I get? For that part b, I simply get 1 over sine multiplied by the derivative of sine, which is cosine. So cosine over sine, and that is cotangent. Yes, guys? I get cotangent x. Everybody sees that? It's the derivative of ln absolute value. It's 1 over what's inside of the absolute value. The derivative of that will be cosine of what's inside. So you get cosine over sine, which is cotangent. Go ahead, guys, and solve, and you can do it very quickly. Can you tell me what is c? What's the derivative of c? Well, careful, guys, careful. Okay, good, good. Risha, good. Come on, guys, faster. Yes, Ibad, good. Okay. Let's see. All right, guys. 1 more minute. Lakey, good. All right, good. So what do? The easiest thing to do here is to notice it's a logarithm. So when you see a power, you can drop it down. So it's really x log base 3 of e. And this is just a number. Yeah, just a number. So it's really just aligned with slope log base 3 of e. So the derivative is simply log base 3 of e, as many of you have written. Good. So next, please calculate d. What's derivative of sine multiplied by ln of 5x? And do it fast, please. Okay, Kirill, good. Sumaya, good. Lisha, good. All right, good. Ibad. Leiki, very good. Yuxin, good. And yeah, good. All right, so let's do it. That's easy, right? The derivative here is the derivative of sine. So I have that y prime is the derivative of sine is cosine of x times ln of 5x plus, you might have observed that ln of 5x can be written as ln of 5 plus ln of x, and that's one way to do it. So then I have here I have sine x multiplied by the derivative of this expression. The derivative of that expression, the derivative of ln of 5 is 0, the derivative of ln x is 1 over x. So we have that. And of course, guys, one thing, are you ready? Don't forget, you see we have sine x times 1 over x. We can simplify, right? We can just take this x and cross it out and write our final solution as cosine x ln of 5x plus sin. Yes, you all agree? I want you to confirm if you agree with me that you can simplify the x there. Okay, Leiki. But the question is, why do you put a question mark, right? Or is it a question? But does it need a parameter or what? I asked simply, did I solve it correctly, right? You agree that I can simplify x and x. Hmm? Why is it taking you so long to call out bullshit? Bullshit. Sine it's a sin, it's meaningless. How can I access the belly? This is terribly, terribly wrong. Terribly wrong to do that. Is that the reason you're wearing masks? I think so. That's fine. But the expert said dip my face in acid, right? It's good for my skin. It's exfoliating. Anybody? All right, guys, those no problem E. You should see, guys. I hope you do see that with sine, right? I cannot access. It's not x that I simplify. There is no algebra. What does sine do to the x, right? And sine by itself is meaningless. It's sine is an operation. It says do something to this x. Okay. So now solve E. What's the derivative of log base 5 x e to the x? Faster. Bewegung, keine Zeit verschwenden. Move, don't waste time. Right? What is that, guys? Okay, so look at it. Yes, you can simplify maybe something, right? So it's log base 5. Careful, it's log base 5, right? X e to the x. What do? You don't want to start taking the derivative right away. It's much nicer. Look at it, right? It's much nicer to write it as log base 5 of x plus x log base 5e. And that's just a constant. Am I right? So what's the derivative of log base 5 of x? It is the derivative of log base 5 of x would be what? Would be 1 over x ln 5 plus this derivative is simply log base 5 of e. I'm done. Good? Everyone understands? Come on, guys, fast. We need to move. Solve problem F. Problem F, please, fast. All right. All right, let's do it now. So here is what happens. So first we are using logarithmic properties to write it in a form that does not involve as much multiplication and division. And then we take the derivative. Derivative here, it's 5. Derivative of the inside is 2x plus 1. Numerator is 2. Minus 1/2 2x over x squared plus 1. This is what we get. Good? Here are some new tasks, guys. Let's see how quickly we can calculate it. First, tell me what's the derivative. This is some number a. Y equals x to the a. Find the derivative, please. So go a, b, c, d, e, f, please. Wonderful, Kirill. Maybe write A, B, C, A answer, B answer, C answer, so that we all know what it is. So try to solve. Look at it. A, B, and C first. Thank you, Ibad. Thank you, Sumaya. Now, how would you solve question C is the problem, right? So A and B, I'm assuming you kind of figured it out. What do I do for C? Thank you, Zakia. So A and B, I would like you to write together, okay? Because I think you know how to take A, and I think you know how to take the derivative for B. Write them together. Let's see. Okay. All right. Let's proceed. So A and B, I imagine you know how to solve. How do you find the derivative of C? You see, it's x to the power of x. Why not take logarithms of both sides? So ln of y will then be equal to ln of x to the x. And the reason you think to do so is because you can take this x and move it down. Yes? So then you have that derivative of ln of y is 1 over y prime will equal to derivative of x down. So, you know, because it would be pretty much x ln x. Derivative of product here, it's ln x plus x multiplied by 1 over x, which is ln x plus 1. Good? Ln x plus 1. That means that for C, what I have to do is just multiply by y. You see 1 over y prime is ln x plus 1. Multiply by y both sides, which is x to the x. I have that the derivative is the original function x to the x multiplied by ln x plus 1. Good, that's for C. A and B we kind of covered. Now, what's the derivative for D? Please calculate the derivative for D as quickly as you can. You see, guys, I hope you are solving it. Just as we're doing it, I'm giving Russian lessons in parallel. So come on. What's the derivative of y x to the sine x? That is, the derivative here is, so what you do is you just simply, let me actually scroll it, easier to scroll down. For d, I apply logarithm of both sides, and that allows me to drop the sine x. Everybody understands? Logarithm of y, here I'll write it just in case. Ln of y is ln of x sine x. And the reason I think to do so is because I can use the logarithmic property to drop down the sine x. Good? That means that we have ln y equals sine ln x. Sine x ln x. Now the derivative is product rule. So derivative of ln is 1 over y prime. Derivative of this product rule, it's cosine ln x plus the derivative here, it's sine over 1 over x. And then all you do is just multiply that result by y. And y is equal to x sine x. Yeah? And that's what and then we have this answer. X sine x ln of x to the cosine x plus sine x over x. Good? Come on, guys. Now I want to know what is the derivative of e. Can you take the derivative of e? It's e to the power of x to the power of x. Can you take the derivative of that, please? E to the xx, you see? So it's e to the power of x to the power of x. Calculate the derivative. All right, calculate e, please. All right. Where are we now? All right, good, Irvin. All we can do, look at it. It's very simple. We already know how to take this derivative. It's not so hard. We have here the derivative is x to the power of x ln x plus 1. So the answer should be what? The answer should be e to the power of x to the power of x multiplied by x to the x ln x plus 1. Yeah, that would be our derivative. Okay, so I suppose for today our time is up, and all I can do is play you the reason why you will be sitting here on Thanksgiving doing more math. So let's do that before you leave. Yes, let's say. So let's hear that song. 1 second.